An explanation of the deflate algorithm by Antaeus space Feldspar. This article was originally posted to comp.compression on August 23rd, 1997. It's important before trying to understand deflate to understand the other two compression strategies that make it up: Huffman coding and LZ77 compression. Huffman coding. Huffman coding is a form of prefix coding which you may not think you know, but you've almost certainly used a prefix code -- when using the phone. Starting from the dial tone, you press a sequence of what may be 5, 7, 8, 11, 12, or some other number of keys, -- and each sequence of keys reaches another specific phone line. Now, suppose you're in an office with a internal switchboard, as many large companies do. All of their phones within the bank only require 5 numbers to dial instead of 7 -- That's because it's expected that you'll be calling those numbers more often. And you may still need to call other numbers, though, -- so all of those numbers have a 9 added to the front. That's a prefix code. Each element that you could want to specify a code made up of numbers, and because no code for one element begins with the code for any other element. You can type in that code, and there will be no ambiguity about that being the one you mean. A Huffman code is a prefix code prepared by a special algorithm. Here, instead of each code being a series of numbers between 0 and 9, each code is a series of bits, either 0 or 1. Instead of each code representing a phone, each code represents an element in a specific alphabet, such as the set of ASCII characters, which is the primary but not the only use of Huffman coding in Deflate. A Huffman algorithm starts by assembling the elements of the alphabet, each one being assigned a weight, -- a number, that represents its relative frequency within the data to be compressed. So the weight is the frequency. These weights may be guessed at beforehand, or they may be measured exactly from passes through the data, or some combination of the two. In any case, the elements are selected 2 at a time. The elements with the lowest weights can be chosen. The 2 elements are made to be leaf nodes of a node with 2 branches. I really hope you know what node trees are, .. Anyways, suppose we had a set of elements and weights that look like this. And we have 2 columns, 1 column of letters and 1 column of weights. We have A, B, C, D, and E, 16, 32, 32, 8, and 8. So A is 16, B is 32, C is 32, D is 8, E is 8. We would pick D and E first because those are the lowest values, and make them branches of a single node. So we would pick D and E first and make them branches of a single node, -- one being the 0 branch and 1 being the 1 branch. Alright, so we have an empty node, and then it branches off in the left direction for 0, in the right direction for 1, going to either D or E respectively. At this point, no element has been given its complete code yet, but we now know that the codes for D and E will be exactly the same, except for the last binary digit. D will end with 0 and E with 1. So we are building this tree in reverse, is what it looks like, which is different than what I've seen in tutorials, so this is good, because it's different. The combined node D and E is placed back with the other, as yet uncombined elements, and given a weight equal to the sum of its leaf nodes. In this case, 8 plus 8 equals 16. Again, we take the 2 nodes with the lowest weight, which are A and D - and -E, and join them into a larger node. Okay, so now we have a larger tree. So we have that original DE at the bottom, and now the DE section is the left leaf of a new root node, and A is the right leaf of the new node, So right now we know that D, the ending binary for D is 0, 0, and the ending binary for E is 0, 1, but we don't know what binary could possibly come before that. At this time, when the node A-D-E is put back into the list of elements, all remaining elements have the same weight, 32. Which two of the three are selected to be combined first is not important, at least not in the classical Huffman algorithm. So they're saying not in the classical Huffman algorithm because canonical Huffman codes would want you to do something where there's a lexicographical ordering and probably alphabetical in this case. When all nodes have been recombined into a single Huffman tree, then by starting at the root and selecting 0 or 1 at each step, you can reach any element in the tree. Each element now has a Huffman code, which is the sequence of zeros and ones that represent the path through the tree. Now, it should be fairly easy to see how such a tree and such a set of codes could be used for compression. If compressing ordinary text, for example, probably more than half of ASCII character set could be left out of the tree altogether. Frequently used characters like E and T and A will probably get much shorter codes, and even if some codes are actually made longer, they will be the ones that are used less often. However, there is also a question: how do you pass the tree along with the encoded data? It turns out that there is a fairly simple way, if you modify slightly the algorithm used to generate the tree. In the classic Huffman algorithm, a single set of elements and weights could generate multiple trees. In the variation used by the Deflate standard, there are two additional rules. Elements that have shorter codes are placed to the left of those with longer codes. In our previous example, D and E wind up with the longest codes, and so they would be all the way to the right. Among elements with codes of the same length, those that come first in the element set are placed to the left. If D and E end up being the only elements with codes of that length, D will get the 0 branch and E the 1 branch, as D comes before E. So I think they're talking about the lexicographical sorting. It turns out that when these two restrictions are placed upon trees, there is most one possible tree for every set of elements and their respective code lengths. The code lengths are all that we need to reconstruct the tree, and therefore all that we need to transmit. LZ77 compression. Oh, okay, so there's an algorithm. So I was thinking about the above paragraph. So there's an algorithm where if you properly sort the characters lexicographically and also by frequency or weight, and to use this algorithm, you can get the correct Huffman codes without actually having to generate a tree. And it's like a canonical Huffman codes formula, which I believe is used in the PNG compression, or PNG, yeah, in the PNG compression and decompression. LZ77 compression. LZ77 compression works by finding sequences of data that are repeated. The term sliding window is used. All it really means is that at any given point in the data, there is a record of what characters went before. A 32K sliding window means that the compressor and decompressor have a record of what the last 32,768, and then within parentheses 32 multiplied by 1024, characters were. When the next sequence of characters to be compressed is identical to one that can be found within the sliding window, the sequence of characters is replaced by two numbers: a distance representing how far back into the window the sequence starts, and a length representing the number of characters for which the sequence is identical. I realize this is a lot easier to see than to just be told. Let's look at some highly compressible data. Blah, 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 and blah with a, what do you call it? A not symbol. What is the real word for that? Exclamation mark. Our data stream starts by receiving the following characters. And so it's just saying BLAH, but it's quoting those and putting it in a parenthesized list. And B. However, look at the next 5 characters. Okay, so we got a little diagram here of the next 5 characters, and it's an exact match. Yep, an exact match. Even with that space? Well, maybe not with that space. I don't know. LAH space BL. LAH space BL. LAH space BL. Yeah, so that is, yeah, okay, so there's an exact match right there. There is an exact match for those 5 characters in the characters that have already gone into the data stream, and it starts exactly 5 characters behind the point where we are now. That being the case, we can output special characters to the stream that represent a number for the length and a number for the distance. The data so far, so the data that so far has been read from the stream is blah, blah, and then a B. The compressed form of the data so far is going to be blah space B, and then distance equals 5 and length equals 5. Because we're going to go back, we're going to jump back 5. So 5, if we jump back 5, I'm going to try this for a second. So let me go over here. Okay, jumping back 5. So we're at B. 1 jump is on the space. 2, 3, 4, 5. We get back to that capital B. I'm not sure if that's correct, because I feel like maybe what they mean by a jump back of 5 is 5 is like 1 is where you are, 2, 3, 4, 5. Okay, so I guess I'm not sure if that's the way the algorithm is supposed to work, because I thought that a jump back of 0 was when you did like a run line repetition of the current character. Oh no, they mean, okay, I see what's going on here. We are here, and so we're going to jump back 1, and this is our jump back 1. Here's our jump back 2, here's our jump back 3, 4, and then 5. So we are here, we're not here, but we start here, and that's why, okay, that makes sense, okay. So let's keep on reading. So scrolling, okay. The compression can still be increased, though. To take full advantage of it requires a bit of cleverness on the part of the compressor. Look at 2 strings that we decided were identical. Compare the character that follows each of them. In both cases, it's L, dash dash, so we can make the length 6, not just 5. But if we continue checking, we find the next characters, and the next characters, and the next characters are still identical, even if the so-called previous string is overlapping the next. Even if the so-called previous string is overlapping the string we're trying to represent in the compressed data. Oh, got you. So there's some self-referentialness going on there. That's interesting. Because eventually, so what it's saying is that as you reference backwards with this, eventually it could be like going here, here. Like if you had a really long length here, it could be looking at this, and then maybe it's taking this, and then 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 it can start to take some character from inside here, another character from inside here, and another character from inside here. If this length, right? So basically if the length is more than the distance, you could get some like overlapping. And I get why that would be allowable, but I also get why that might make the algorithm a little bit confusing and quote-unquote clever. Let's keep on reading. It turns out that the 18 characters that start at the 2nd character identical to the 18 characters that start at the 7th character. It's true that when we're decompressing and read the length distance pair that describes this relationship, we don't know what all those 18 characters will be yet, dash dash. But if we put in place the ones that we know, comma, we will know more, comma, which will allow us to put down more, dot, 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 or, comma, knowing that any length and distance pair where length is greater than distance is going to be repeating distance characters again and again, we can set up the decompressor to do just that. It turns out our highly compressible data can be compressed down to just this. We have blah space b, and then distance equals 5 and length equals 18, then an exclamation mark. Basically, I believe this is a when the length is more than the distance, you're going to have like some modulus math going on. Because even though it's kind of confusing to think about that self-referentialness, all it really is boiling down is run-line repetition of whatever these 5 characters are. So these 5 characters will just get repeated over and over again. Does that make sense? Am I correct there? Or am I... No, that's correct, yeah, because if this is more, then the only way, if this length is greater than this distance, then the only new characters you could ever get after you go past 5 here would be the first 5 characters. So when the length is more than the distance, it's just a run length repetition of these 5 characters, whatever they happen to be. I could be off by 1 when I say those 5 characters. But let's keep on reading. Putting it all together. The Deflate compressor is given a great deal of flexibility as to how to compress the data. The programmer must deal with the problem of designing smart algorithms to make the right choices, but the compressor does have choices about how to compress the data. There are 3 modes of compression that the compressor has available. 1. Not compressed at all. This is an intelligent choice for, say, data that's already been compressed. Data stored in this mode will expand slightly, but not by as much as it would if it were already compressed and one of the other compression methods was tried upon it. 2. Compression, first with LZ77 and then with Huffman coding. The trees that are used to compress in this mode are defined by the Deflate specification itself, and so no extra space needs to be taken to store those trees. 3. Compression, first with LZ77, and then with Huffman coding with trees that the compressor creates and stores along with the data. The data is broken up in blocks, and each block uses a single mode of compression. If the compressor wants to switch from non-compressed storage to compression with the trees defined by the specification, or to compression with specified Huffman trees, or to compression with a different pair of Huffman trees, the current block must be ended and a new one begun. The details of how the LZ77 and Huffman work together need some closer examination. Once the raw data has been turned into a string of characters and special length-distance pairs, these elements must be represented with Huffman codes. Though this is not, not standard terminology, call the point where we start reading in bits as a dial tone. After all, in our analogy, the dial tone is where you can start specifying a series of numbers that will end up mapping to a specific phone. So, call the very beginning a dial tone. At that dial tone, one of 3 things could follow: a character, a length-distance pair, or the end of the block. Since we must be able to tell which it is, all the possible characters, literals, elements that indicate ranges of possible lengths, lengths, in quotations, and a special end-of-block indicator are all merged into a single alphabet. The alphabet then becomes the basis of a Huffman tree. Distances don't need to be included in this alphabet, since they can only appear directly after lengths. Once the literal has been decoded, or the length-distance pair decoded, we are at yet another dial tone point, where we can start reading again. If we got the end-of-block symbol, of course, we're either at the beginning of another block or at the end of the compressed data. Length codes or distance codes may actually be a code that represents a base value followed by extra bits that form an integer to be added to the base value. Probably the trickiest part of Deflate specification to understand is the way trees are encoded to go along with the data, and when that data is compressed with specialized trees. The trees are transmitted by their code lengths as previously discussed. The code lengths are put all together into a sequence of numbers between 0 and 15. The Huffman trees that are created must be kept to code lengths of no more than 15. This is the tricky part, not the part of constraining the order of the elements. Not all elements have to be given code lengths if the last element of the alphabet are of 0 code lengths. They can and probably should be left out. The number of elements in each of the two alphabets will be transmitted, so the trimmed alphabets go together in a single sequence. Once the sequence of code lengths is assembled, it is compressed with a form of what is called run-length compression. When several elements in a row have the same code length, often 0, special symbols may be used to indicate the number of elements with this code length. Our sequence is now a sequence of numbers between 0 and 18, possibly with extra bits forming integers to modify base values, comma, as was the case with the length and distance codes. A Huffman tree is created for the alphabet of 0 to 18. Psi? Okay. The sequence of 0 to 18 codes and extra bits is prepared with the Huffman codes replacing 0 to 18 elements. This Huffman tree needs to be included with the data. Of course, like the other Huffman trees, it will be included by recording code lengths of the elements. However, once again, psi, all capitals, with asterisks, they are not recorded in the order 0, 1, 2, 3, 4, 16, 17, 18. They are reordered in a special order. 16, 17, 18, 0, 8, 7, 9, 6, 10, 5, 11, 4, 12, 3, 13, 2, 14, 1, 15. The logic behind this is that the elements near the end of the sequence are most likely to have 0 code lengths, i.e. not be in the tree at all, if they are indeed 0. They can be trimmed from the end of the sequence. The number of elements that are being directly recorded is also included in the data. Don't quite understand that. Maybe if I put these numbers into a tree and then traverse the tree, maybe I would understand what's going on here. Yeah, because 1 and 15, 2 and 14, 3 and 13. Yeah, okay, let me look at this for a second. So 1 and 15, 2 and 14, 3 and 13, 4 and 12, 5 and 11, 6 and 10, 7 and 9, 0 and 8, 17 and 18. Okay, yeah, so what I'm seeing right here is, yeah, so there's a definite pattern here, right? Because we got 15, 14, 13, 12, 11, 10 interlaced with 1, 2, 3, 4, 5, and 6, blah, blah, blah. Yeah, so I think if I were to try to look at a tree view of this, maybe it would make more sense, which I might try later. The logic behind this is that elements near the end of the sequence are most likely to have 0 code lengths, i.e. not be in the tree at all, If they are indeed 0, they can be trimmed from the end of the sequence. The number of elements that are being directly recorded is also included in the data. Those are trouble points. I think for the Deflate spec, along with the specification itself and a bit of time, it should hopefully clear things up. If you have any other questions, please ask. And then it has their name again, which I cannot pronounce, so I will not try. It's Antaeus Feldspar, and that is Feldspar at netcom.com. And click here to return to the zlib homepage, last updated 13 April 2002, and then a little copyright notice.